Should I use the microphone or this?
That seems to be working better, but if you prefer the microphone, you're
All
welcome.
right. Hi, everyone. So a common theme in our research lab, and I guess everybody who's been presenting today, is using some form of AI or machine learning in order to do inverse design. We will be showing a method that we have done. We have published a paper on that involves using reinforcement learning to optimize the design of an acoustic cloaking device comprised of several cylindrical scatterers. My name is Tristan Shaw. I'm a graduate student at San Jose State University, and I'm studying artificial intelligence. And this work is going to be elaborating on our paper that we published last year under the supervision of Dr. Firuza Mirkalova, and Peter Lai was also on this project, and several others who could not attend today. So the outline that I'll go through for my presentation is first introducing acoustic metamaterials. I'm sure most of you are already familiar with this. This was new to me because I'm coming from an AI/data science background. Then I'll go over reinforcement learning, total scattering cross-section, which is our metric we're trying to optimize in our design, our problem formulation, how we use reinforcement learning in order to solve this problem, and then numerical results related to the positional design that we did, and also the radii adjustment design that was successful as well. And then finally, some computation time and drawbacks and a conclusion. So acoustic metamaterials are a type of engineered material which has one or more special property that make it useful beyond a traditional manufactured substance. They have many properties listed here, but the ones we care about is the wave interaction between the metamaterial and an incident wave. This diagram here shows a use case of such a material. In the center of the figure, we have our acoustic scattering devices, which are randomly configured on the left. And of course, they're causing quite a bit of scattering because they have not been optimized for position yet. So you see backscattering in the figure and also some wave disturbances. But the figure on the right, however, is showing the results of the optimized configuration. There's still some disturbances, but they have been suppressed to a lower level by our reinforcement learning algorithm. So inverse design, I think that you've all gotten a thorough introduction to what that is. Basically, we're using some kind of algorithm in order to design a device. And this is important because we can no longer use intuition to optimize these designs when they get so complex. We add more acoustic scatterers, we have large metasurfaces. It becomes very difficult to do. So there's several approaches, such as gradient-based optimization, topology optimization, and these are older approaches, but our research lab is focused more on applying new AI-based approaches to this inverse design problem. So Peter did generative adversarial networks, and for this project we were using reinforcement learning. So reinforcement learning is a process where it focuses on sequential decision-making in some sort of environment. Deep reinforcement learning is an extension of this, where we use deep neural networks as a universal function approximator to assist the reinforcement learning process. So in this setup, we'll have some sort of environment, and we have a representation of the state of this environment, denoted as ST. This state gets passed to the agent, which uses this to inform its selection of an action based on value. It learns a value of these actions. Once the action is selected, it is sent to the environment, which responds and produces a next state and also a reward. This is what informs the agent what is good and what is bad. So this cycle repeats over time, and hopefully the agent will learn how to select more optimal actions. Reinforcement learning has taken off in recent years and has achieved mastery over games such as chess and Go, and humans can no longer even compete with these agents. But not only have they been applied to discrete zero-sum games, they've also been applied to inverse design. In Baldo et al. 2020, they used reinforcement learning agents to design a photonic absorption device. And they had a repeating structure where they had these design parameters, thickness of a plate, as well as certain properties of these ellipsoid structures. Subsequently, in 2021, our research group at San Jose State University executed the first application of reinforcement learning to acoustic metamaterial design, and I'll go over that more in a second. So what we were trying to optimize in order to make a cloaking device is the scattering produced by a configuration. If we can reduce the scattering to 0, then we've effectively created an acoustic cloak. So we're using a metric known as total scattering cross-section. It is a number which is calculated at a specific wave number, Ka, and if it goes to 0, then it passes through whatever configuration exists undisturbed. So now I'll go into our problem formulation. This is an expanded version of the reinforcement learning diagram I showed previously. It's split up into two components, the environment and the agent. The environment has some subcomponents. Firstly, a physics simulator. We model our acoustic scatterers as circles and apply some physics laws on them to allow the agent to move them around in a natural way, as if it's experimenting on its own. And also this prevents collisions, overlaps, especially as we add more cylinders. And then, of course, the reward function is very important. In our case, we use total scattering cross-section, but we make the reward negatively proportional to this scattering so that when the agent raises the reward, we lower scattering. Then we have the reinforcement learning agent part of it. It's comprised of two neural networks. The first is a Q network, which estimates values of actions. And this is the agent's policy. It selects actions directly from this network. So based on which action shows that it's the highest value. This is in one basic algorithm. We tested multiple ones. And then the target Q network is used in updating this Q network. It's not directly involved in decision making. Finally, we have a replay buffer, and this is the agent's memory. So as it's experiencing its environment, it's adding data to this buffer and then sampling it repeatedly in order to perform updates to the Q network. So yeah, these are the major components of a simple RL algorithm. This was not the best algorithm, just the easiest to explain. And now here is the result of a fully trained algorithm. This is a looped video where it's starting from an initial random configuration, and it's iteratively adjusting the scatterers. And you can see on the right the total scattering cross-section computed at a range of wave numbers. It starts very high at the beginning. I'll tell you when. Yeah, that was the beginning. It drops off rapidly, and then it settles into a low minimum. We compared the results of our algorithms to a gradient-based optimization algorithm known as fmincon. This just shows the DDPG algorithm. It's a different reinforcement learning agent type. But you can see they start at the same initial random configuration with a large amount of scattering, and both algorithms are able to successfully reduce that scattering to a low level. RL agents are able to successfully compete with a mature state-of-the-art gradient-based optimization algorithm quite favorably, but it kind of starts to diverge as we increase the number of scatterers. The design space grows exponentially. But it's worth noting for the 6-scatterer configuration, DDPG was able to reduce it lower than fmincon. So I think this foreshadows potentially making a reinforcement learning system that is better globally than a gradient-based one. Not only did we apply this methodology to a positional task, we applied it to a radii adjustment task with fixed position cylinders around a static core. In this case, we did not have the gradient of the objective function with respect to the cylinder radii available. So our reinforcement learning algorithm was able to learn how to adjust these scatterers in a intelligent way to reduce the overall wave scattering. And this figure on the right shows the training of our model over the whole course of its training cycle. It would play episode after episode, and we logged the lowest scattering configuration it discovered each episode. So as it's training, it's going down and stabilizes at a minimum. Like I mentioned, the gradient-based optimization algorithm was not even applicable in this situation, but I compared both of our reinforcement learning algorithms we tested here, and they both were able to successfully optimize the design. When we first started doing our research, we wrote everything in Python and called a MATLAB script through its engine. And this was very bad. It resulted in long training times, up to 2 days, especially as we increased the number of scatterers. But since then, in recent months, I've ported all of our research code over to Julia, and we're getting a massive speed increase, as you can see here. Julia runtimes of a single call to the objective function are shown in blue, and MATLAB is shown in red. This is not even counting the overhead, so you can somewhat visually see that MATLAB is scaling exponentially or polynomially, and Julia seems to be scaling linearly at low numbers of scatterers. So this is allowing us to increase design complexity and just allow us to brute force a little bit more out of our algorithms. So in conclusion, reinforcement learning was capable of suppressing this very complex acoustical function for both positional and radii designs. These methods do compare well against a very mature algorithm that's been around for a while and has a lot of support. These are preliminary results, and they're comparing favorably. Switching to Julia was an excellent move, it turns out. We saved a lot of computation time, so if anybody else is struggling with the overhead of calling in MATLAB, you might want to check out this language. It has speeds more similar to C++ without all of the difficult syntax. And then in future directions, my thinking is that we are going to create a framework which allows us to apply reinforcement learning to any inverse design task and try to generalize this as much as possible so that it can be an off-the-shelf tool that we can offer to researchers in acoustics or any other field. So thank you. That's it. If anybody has questions, I'd be happy to answer.